Welcome, my name is Michael Schwarz. I'll be presenting some work that I did together with Simozan, Helmut Seidel, Kalmar Apines, Julian Erhardt and Vesal Vojdani on improving thread-modular abstract interpretation. Most programs nowadays are multi-threaded, so one wants to analyze them. What makes this complicated is that multi-threaded programs often use mutexes and dynamic thread creation. They might use complicated control flows such as waiting and signaling, and quite often they also have thread joins. The analysis of multi-threaded programs is challenging, and one reason is that the product construction, which one would intuitively want to do for analyzing such programs, encounters a couple of issues in this setting. The first issue is well known, it's this issue of the combinatorial explosion. This is made even worse by the fact that for an interprocedural analysis, it does not suffice to simply maintain one program point per thread, but one would in theory have to maintain an entire call stack per thread. And the final issue that this product construction suffers from is that it's very hard to handle dynamic thread creation in such a setting. So what one actually wants to do in such a setting is one wants to have a thread-modular analysis, and the dream there would be that one has an analysis and one simply analyzes each thread completely in isolation of all the others, and this would then give us an analysis that scales linearly with the number of threads, or maybe with the number of different classes of threads that one has in the system. However, programs do actually interact via globals and such, so it's not completely possible to actually analyze each thread completely in isolation, so one actually has to take some effects of other threads into account. So let's describe the setting for this concrete work. So as we said, we have multi-threaded programs, and what we're interested in for now is the values that one reads for globals. We will contrast two different approaches to this that one finds in literature. The first one being the so-called Vojdani-style approach. The idea there is that one accumulates all writes that are visible to other threads at an unknown G for a global G, and one does local updates where no other thread can interfere. Now the question, of course, is what is visible, and here this works by computing a set of mutexes that is held at every access to a global, and this one calls the set of protecting mutexes. And now whenever all protecting mutexes are held, a write that a thread does locally is not visible yet, and it can happen completely locally and only needs to be published once the corresponding mutex is unlocked. So let's take a look at a small example here. We have our program again, this time annotated with the log sets for each program point. The first step here would be to compute the set of protecting mutexes. So one would look at all of the places where this global G is accessed, and then one would look at the log sets at these places and simply take the intersection. So the protecting log set here would simply be B. And then what one looks at are the unlocks that happen after a thread has written to a global. So for example, this one here. And here one needs to publish this local value that G might be 0 to this unknown. And the same applies for the other unlock being the other thread. And here one will publish this value that G might be 17. What's important to notice here is that this value G equals to 42 does not need to be published here, because it's completely local and has been overwritten before these protecting mutexes were giving up. And then when one actually wants to find out the value that we read for x, we would simply consult this unknown again and find that the value for x that one reads is either 0 or 17. Now what we have already seen while we were doing this example is that we found it convenient to accumulate flow and context insensitive information for this global G while we were doing an analysis that is context and flow sensitive. A very convenient way to formalize this is by using what's called side effect and constraint systems. So these are regular constraint systems that are then enhanced with side effects. What are side effects? They are contributions to other constraint system unknowns that are triggered during the evaluation of a right-hand side for a given unknown. So to go back to our example, we had the situation where in the local state we had this value of G is 17 and we did an unlock B. So what one would do here is one would compute the local state of the successor. So in this case it would stay the same. And then the side effect was that we also side effected this value of 17 to this unknown G. So this would be the side effect here. And how can one write this down? A possible way to write this down is given here. So one would first of all calculate the new local state sigma prime. And this would be the second component of this tuple, so this is a contribution to V. And then the first component of this tuple would be a set of side effects. Now that we have seen this Vojdani style of analysis, the other style of analysis goes back to Antoine Miné and his collaborators. The idea there is that one propagates the values from an unlock to a lock, provided that some appropriate side conditions are met. Now the setting that we're looking at here, just to recall quickly, is we're looking at non-relational value analysis and no thread IDs. What does this look like in our example? Well, for the simple setting, the side condition boils down to checking that there's no overlap between the locks held after an unlock and the locks held at the corresponding lock. And then one will propagate information from unlocks to locks. So here one will propagate this information that G is 42 from the unlock A to the lock A in the other thread. And there one would merge this value of 42 into the local state, provided that the side condition is met, which it is here, because the intersection of B and the empty set is once again the empty set. So one can do this for all unlock and lock pairs. And then one ends up with something that looks like this. And now if you want to determine the value that we actually read for x, we need to see which values are merged into the local state via join. And this is once this value that G equals 42 that is merged at the lock A, and this value that G might be 17 that is merged in at the lock B. So what is quite interesting here is that in this case, this Miné style analysis is actually less precise than the Vojdani style of analysis. This is not purely a coincidence, but we have in fact sort of maliciously constructed this example to highlight an insight that we had, namely that this Miné style analysis and the Vojdani style of analysis are actually incomparable when it comes to precision. This insight was the jumping off point for the rest of our work. First of all, to do a fair comparison, we had to both formulate them in a common framework, and we found out that this framework of side effecting constraint systems that we have just introduced is very well suited for this task. Then we also want a systematic approach to construct soundness proofs for these types of analyses, and we do this with respect to a local trace semantics, which is a new concrete semantics that we give. And then we also provide improved versions of each of these analyses. And finally, we have also done a preliminary experimental evaluation. What does our concrete semantics look like? Well, we wanted it to be a trace semantics because the collecting semantics is not expressive enough to conveniently argue about a lot of these more involved analyses. And we also wanted to be a local trace semantics. We'll get into what that means in a second. But basically the idea here is that the concrete semantics should also be thread modular, just like our analyses, and should in general match the analyses as closely as possible. Before we talk about local traces, let's maybe talk about global traces. And one might choose to represent a global trace maybe as simply a sequence of executed edges that are always labeled with which thread took them. So one could have, for example, have this example where the first thread first executes this create edge, then the second thread does the lock and sets the global to some value, and then the second thread does the unlock, and then it's the turn of the first thread again, who then locks A, and then maybe this local Y is set to 7. So this could be some sort of representation of a global trace. Then in contrast, what is a local trace? Well, for a local trace, one would take the standpoint of one thread, which we call the ego thread, and only those things that the ego thread has knowledge of are actually in this local trace. So in some sense, instead of having a bird's eye view of the system, where one sees the local states of all threads, one takes the perspective of only one of these threads. So let's take a look at an example. This is a local trace of the first thread that ends in this unlock A. And this thread is aware of its own history and is also aware of parts of the history of the other thread, namely that part which it has learned about by communicating via locking and unlocking of this mutex A. However, it, for example, does not know whether this other thread has executed this step where it sets this local variable y to 7 or not. So quite surprisingly, one can also very nicely formulate this concrete semantics in a side-effecting manner. And then one ends up with unknowns u for program point u, where one stores all local traces that end in this program point u, and unknowns a for a mutex A, where one stores all local traces that end with an unlock of this corresponding mutex. Then what does the right-hand side look like for locking and unlocking? It looks somewhat like this. So at unlock A, on top of the traces that reach the program point before this lock A is executed, one also takes the traces into account that were stored at this unknown A. and one then incorporates some of them and combines them. And for an unlock A, by the same token, one computes the new set of local traces for the successor node. And since they now also end with an unlock A, they need to be side effected to this unknown A. Let's take a look at an example. So this is our example program. We have one trace at this program point U, and we have two traces at this stored at this unknown A. And then to obtain the traces at this program point V, so the immediate successor, what one does is one takes the local trace at the program point U and combines them with one of the local traces at this stored at A. So for example, this one, you can combine these two and then end up with a new local trace. This would be a resulting local trace. However, not all of them are compatible. So for example, the second local trace that appears here, one could not combine them. So it would also not appear in the result here. What is also very interesting is that once one has formulated this concrete semantics, one also sees a very close connection with this Miné style of analysis when one formulates that in a side-effecting manner. Namely, where we have unknowns U for a program point in the concrete semantics, in a side-effecting formulation of this Miné analysis, one would have unknowns U and S for program point U and log set S, and where we have unknowns A for mutexes A, in our concrete semantics for a Miné style analysis, one would have unknowns G, A, S for a mutex A, a global G, and the log set S that was held after the unlock of this A. Having cast all of these analyses in a common framework, we also have identified some possibilities for improvement for either style of the analysis. For example, in the Miné style analysis, one wants to get rid of eager reading, that is incorporating the values already at a lock, and instead delaying this until a global is actually accessed. And by this, one can often exclude some flows and become more precise. On the other hand, for this Vojdani-style of analysis, the obvious limitation to lift is requiring one set of protecting mutexes for all accesses. To achieve this, we give some ingredients for more precise analyses. The first thing is that for globals, on top of this G, A, and S that we already used for the side-effecting formulation of Miné's analysis, one can also track this log set W there. That is the log set that is held when one writes G. And in the local state, one can additionally track some information for each global. For example, one can track the set WG of log sets held when last writing to G. One can also track this set PG of log sets that was held since last writing to G. And additionally, one can also track some information for each mutex. So one can track the set LA of background log sets held when last acquiring A, or the set VA of globals that must have been written locally since last acquiring A. And with these ingredients, we have then devised some more precise analysis. So the baseline here are the Miné analysis and the protection-based analysis, which is a Vojdani-style analysis. And then we give a log-centered analysis that uses L and V and is an improvement of Miné's analysis. And we also give a right-centered analysis, which uses W and P and improves on the protection-based analysis. However, it turns out that they are still incomparable, so we also give a combined analysis that actually makes use of all of these four data structures. Having formalized all of these analyses in a common framework then also allowed us to do a preliminary experimental evaluation, which we did within the Goblint static analyzer for multithreaded C. In total, we have looked at 13 programs here that range between 600 and 3,000 lines of code. When one looks at the runtime, what is interesting is that this protection-based analysis is up to an order of magnitude faster than the other analyses, and for the other analyses, their runtime simply increases with how complicated they are. So the other dimension which is interesting to compare along is precision, and here our takeaway seems to be that sophistication does not really pay. So for our benchmarks, all analyses had identical results for 11 out of 13 of these, and for the remaining two benchmarks, there was only marginal differences, where Miné's analysis was less precise at 6%, respectively 16% of the global reads, and all other analyses were equally precise. However, this conclusion mainly applies to the benchmarks that we have seen here, and it may very well be the case that for more complicated programs that use intricate schemes for communication and synchronization, that these more involved analyses actually pay off for these. Some future directions that we would like to take this work in is we would like to explore the potential of the local trace semantics, and in particular we're currently looking at relational analysis and also at analysis that take thread IDs into account. And with this, I'd really like to thank you for your attention, and I look forward to your questions.